One second. So, good evening, everyone. Welcome to the series of lectures on GANs. This is the first lecture in the series, and I'm Gokul. I'm from CS21, and I'm a coordinator of the analysis. I'll be taking the first half of this session, and then Saran, who's also from CS21 and also a coordinator, will be taking the second half. So yeah, let's start. So these are the topics that we'll be going over in the session. I'll be topping the first three, and then Saran will cover the next three. So yeah, so like if you guys had attended summer school, this session will be a cakewalk for you. Like you can easily understand what's going on and stuff. But if you haven't attended summer school, it's completely fine. I'll be going through all the concepts that are required to understand first, and then I'll try to be minimal though, because we don't have a lot of time in the hand. So and then we have to cover the whole thing as well. So yeah. So let's start with the recap of neural network. So basically, what is a neural network and why do we use neural networks? Let's say you have a housing data set, and then you're trying to predict the price of a house. Say what factors do the price of a house depend on? Like what, first the locality obviously, and then what area of the house, number of bedrooms, and then what else, the age of the building maybe, and so on. So like the input vector of the problem is all these features, and the output vector should be the price, and we're trying to find the mapping from the. So a neural network, here there is an input layer, and then here there's an output layer. So input layer will consist of all the features. Like the first node may be the age of the building, the price, or not the price obviously, the what else, the number of bedrooms and so on. And the output layer will only have one node in our problem, will only have the price in our case. So yeah, like what else, like in which cases we might have, do you think we might have multiple nodes in the output layer? Like what, something that I can think of is that if you're trying to make a model which classifies whether a mail is spam or genuine, that will have two nodes, right? One is spam and one is not spam. So it's a binary classification problem. And so yeah, so the structure of a neural network is like this: you have an input layer, you have some hidden layers, and there's an output. So, and each hidden layer, each node of each layer is connected to each node of all the each node of the preceding layer and each node of the succeeding layer as well. And the connections are shown by these arrows here. And then all these connections have some weight, and each node of the hidden layers and the output layer will have something known as the bias. So you have an input layer, and how do you find the value of this node? So what you'll do is that you'll take the input vector and then dot it with the weight vector for that is incoming into this node. So as it's written here, zj equal to summation of wji and times xi. So that's basically the dot product of the input vector and the weights vector. So and then you won't stop there. You will add something known as the bias as well. Like the bias is unique for each. It's not unique, yeah. There'll be something called as the bias for each node. You just add it, and then you'll pause this value into something known as an activation function to get the exact value of this node. So you'll find the values of each nodes of this layer first from the input layer, and then you'll carry on doing that for all the hidden layers, and finally you'll calculate that for the output layer as well, and that's how you get the output. So yeah, and then yeah, as I mentioned here, you have the weights corresponding to this node, and then you have the input vector. You just dot it, and then add something known as the bias, and then pass on this value. and then pass in this value to the activation function to get the value of that node. So yeah, and yeah, as is written here, the weights and the biases are the things which define our model. Like, are the things which determine how well a model performs, like how accurately our model predicts or something. So yeah, and this is an example of how you feed forward. This like forward pass or something. So this is a 28 cross 28 pixel image, and each pixel will have a value, right? Each pixel will have if the pixel is completely black, it will have 0. If it's completely white, it will have 1. And then if it's somewhere in the middle, the value will be somewhere in between 0 and 1, depending on the color of the uh, pixel. So you'll take all that pixels, you'll just write it up in the same order. So 28 cross 28, 20 times 28 is 784. So you'll have that many nodes in the input vector, and then here you have the hidden layers, and then here you have the output layer. The output layer signifies the digit which is represented by the image. So as it's shown here, like we are getting 2 right here, as you can see. So that's how a forward pass of a neural network work. So I say that if we choose our weights and biases correctly, the model will perform well and you'll get the output correctly. But how do you choose the weights? You'll keep on updating the weights during the training of the model. So how do you initially choose the weights? It's random. Like, you can choose any weights, like any values for each of these, and then just start. So basically what we're trying to do is like, think of it like a paraboloid. Like to update the weights and biases, you need to like add a penalty to the model, right? So like if that penalty is known as the loss function. So what we're effectively doing is that we're trying to minimize the value of the loss function. Like, you can think of it like a paraboloid, something a paraboloid, maybe like paraboloid is there, and then the z-axis is the loss function, and then the x and y axis are 2 parameters maybe. So you just start at some random point of that paraboloid, like an upward facing paraboloid, obviously. So you'll just start at some random point of that paraboloid. You'll just traverse through the paraboloid to get the minimum of the loss function. So yeah, that's how you initialize weights, and then like updating weights. So you have the loss function. Our objective is to minimize the loss function, right? So we'll take the gradient of the loss function with respect to that particular parameter. We'll multiply it by some constant known as the learning rate, and then we just subtract it. So we'll get the new weights, and then as you keep on doing this, your model just approaches your weights and biases, approach the optimum value of the weights and biases, and hence your model starts predicting accurately. So and yeah, and I mentioned something called the activation function at the beginning, I guess. So what is this function, and why do we add this? So we're basically calculating gradients, right? So so if you look at here, wait one second. Yeah, if you look at here, the value of each node is just a linear combination of the values of the previous node, right? So if you take gradients, it'll just go on to 0 really quickly, and you won't be able to capture a lot of information from the data distribution. So so in order to like introduce some complexity, we just have a function called as the activation function. We'll just dot the weight vector into the input vector, and then add the bias, and then pass that value onto the activation function in order to get the actual value at the node. So and then just keep updating, as I mentioned, and then this keep the updating process which you're doing is also known as backpropagation. So yeah, keep that in mind as well. So now convolutional neural networks. So convolutional neural networks is used in image processing. Why, like yeah, so why do we need a new class of networks? Like, why do you guys think, is there any thing wrong with the existing simple neural networks? Like basically what we'll do is that we'll try to downgrade the sample in order to make it easier to process. So why do you guys in CNN? So why do you guys think we need CNNs? Like, why can't we just use the simpler neural networks? Any thoughts or any inputs? I mean, okay, so the problem is that if we have a like in this image, this is a 28 cross 28 image, right? But we have many data sets in which the image dimension is much higher. It's like 224 cross 224, I guess. I'm not really sure, but yeah. And then that is black and white, and you can have colored images as well. So RGB, so 224 cross 224 cross 3 as well. So for each image, if you like, then the input layer will be super huge. The number of parameters will also be really high. So you won't be able to like compute it effectively. The time complexity will be really high. So that's why we try to like downgrade the data into a simpler form and then process it. So yeah, that's the purpose of CNN. So how do we exactly downgrade it? Like here's a 5 cross 5 grid, and then you're making it into a 3 cross 3 grid. So how am I doing this? Is that I have something known as the kernel matrix. So it'll have some values, and then take a 3 cross 3 grid, take another 3 cross 3 grid. Like imagine superimposing them, and then by superimposing, I mean like multiply each value of that matrix, and then form a new matrix. Like do that for like move the kernel across the whole image, and then for each traversal you'll get a value, right? So store that into the actual grid. So by this way we're not losing information about the data set as well, but and at the same time we're reducing the dimensions of the data we're processing. So yeah. And then after a lot of convolutional layers, we have something known as the pooling layer. So what this pooling layer does is, like, if I say I have a pooling layer of dimension 2, so not dimension, pooling layer of size 2. So what does that mean is, what that means is that I'm dividing the actual grid into 2 cross 2 squares, and then I'm finding the average of each 2 cross 2 squares, or the maximum of each 2 cross 2 squares. That depends on the type of pooling which I want to select for my model. If I want average, I'll take average. If I want max, I'll take max. So for each of these grids, I'll take the average and max, and then I'll get something that is the pooling layer. And so yeah, I have the pooling layer here, and then it's like a grid, right? Now like while processing, I have an output vector. It's like a vector, so I just want a linear kind of thing. I don't need a grid kind of thing. So I'll just create a vector, and then just write it in the same order it appears. Doesn't matter. So this is not, that layer is known as a fully connected layer. So by flattening, we get a fully connected layer, and then so effectively after the all the convolution layers and the pooling layer and the fully connected layer, we'll have something like this. We'll have like so here, but basically what we're trying to do is that there's an image of an animal, so we're trying to classify it as a cat or a dog or a horse. And then after all this, the values of the nodes as seen here is what, 35.4, 38.1 point minus 5. Like these values make sense, but we want something more concrete, right? So what we do is that we try to find the we try to make we try to convert it using a function. We try to convert it into the probability of these classes by using a function known as the softmax function. Like the softmax function usually is like what you do in a softmax function is that you take that value, you take the exponential, like e power that value divided by the summation of e power all values. So if you sum that up, you get 1, right? So that's what softmax means. So I guess you guys get it. So yeah, the recap is done. So till now, do you guys have any questions, any queries or something? I'll just start from the beginning. Like you can ask anything. Like, and then I forgot to mention this. The more the number of hidden layers, the more information your model captures, and the number of nodes depend as well. And how do you decide the number of hidden layers, and how do you decide the number of nodes in each hidden layer? You do that by trial and error only. Like you'll just try a few outputs and then try for a few data sets and then find the optimum. So yeah, this one's there. And then yeah, this one I explained, I guess. And then this is the forward pass, and then wait initialization, and this is the back propagation as well. And then activation functions, and activation functions, the common activation functions are sigmoid and then relu as well. So yeah, any questions till now? So yeah, so basically that's the recap. So I'll get into GANs now. This is what you guys have been waiting for, I guess. So yeah, so let's start with something known as the discriminative models and supervised learning. So what a discriminative models does is that you have a, let's say you have a data distribution D, and then in that data distribution you have a collection of data points estimated X, and then each data point will belong to a particular class, and then the set of classes, let's call it Y. So what we're trying to do is that what the discriminative model tries to do is that it tries to find conditional probability that given an image, the probability of each class is what we're trying to do effectively in discriminative models. It's just like classifying a set of images into like this image is a cat, and this image is a dog, and this image is a horse, and those kinds of things. So the set of labels is that set of labels in this case is horse, cat, and dog. So yeah, so discriminative models basically classifies all the images into the respective labels, and this is done by supervised learning. Supervised learning is like you have some labels, and then you have something. I explained what a loss function is, right? So you'll find the loss function, you'll try to minimize it, and then you'll backprop, and then you'll update the weights and biases and stuff, and then you find the actual model, and that's called a supervised learning. And then this finding the conditional probability is comes under the class of discriminative models. So yeah, and then this is an image which depicts supervised learning. So you have a set of data, and then each image is an apple or a banana or a orange, maybe, I don't know what the fruit is. So you train your model, and then you randomly give this image and ask the model what is this. And then the model, if you train it properly, it'll say that this is an apple. It'll predict correctly if you train properly. So yeah, that's what supervised learning is. And then okay, so basically what happened is that supervised learning became famous, and then many models were implemented on supervised learning, and then many research papers were released, and so pretty much whatever can be done using supervised models were kind of done. Obviously I can't say that, but yeah, so we wanted to do something more. So yeah, so far so good, but what's next? So what's next is that generative models and unsupervised learning. So in the discriminative models, we had a set of data, and then we had classes, and then we tried to distribute all the data points into the respective classes. Now in this unsupervised learning, what we're trying to do is that we have a data set, and then we are trying to we have a data distribution, and then we are trying to find the actual data distribution itself. We're not trying to find any conditional probability or something, just directly trying to find the actual data distribution. So generative models, yeah, try to learn the actual distribution of the data in the training set. So how do generative models do this? They try to find the regularities and the patterns between different images or something, what similarities between same kind of images, and then dissimilarities between different kind of images. The models try to identify all those and then try to output the output. So yeah. So what do you guys think is tougher? Which one do you think is tougher? Supervised learning or unsupervised? Like, I just explained what supervised is and I just explained what unsupervised learning is. So which learning do you think is tougher? Yeah, it's as you guys are saying, some people are answering it's unsupervised, because in supervised learning, not actually like we're just trying to divide the data into different classes, as it's mentioned here. Like we're just trying to draw a line between this kind of data and this kind of data. We're just partitioning the data set into two kinds here, and then we can do it into multiple kinds, and that is what is known as class. That is what is known as the classification problem of supervised learning. And in unsupervised learning, what we're trying to do is that we're trying to actually like cluster the data set into different clusters. The key difference between unsupervised learning and supervised learning is that you know, like from before that, data either belong to class 1 or class 2. You know that before training. But in unsupervised learning, we don't have the set of labels, right? So we don't even know what classes to divide this into. So we just divide all the data points which are closer into one class. So that is what is known as unsupervised learning, and obviously unsupervised learning is tougher than supervised learning. And yeah, finally we come to GANs. So what are GANs? GANs are generative adversarial networks. What they do is that you have a data set. Let's say you have a data set of images, and then what GANs try to do is that they try to imitate the data set and then create an image. It's not in the data set, but if an outside person comes and looks at the image, he'll say that this image actually belongs to the data set. So yeah. So how they do that is that by again learning the patterns and similarities within the data set. So is GAN a supervised learning problem or an unsupervised learning problem? It's actually a mix of both. It's not purely supervised either and not purely unsupervised either. So yeah. So and then so this guy. So I'll be honest with you guys right now. So I had no clue who this guy is when I added this image, but then I went and obviously Googled who he is. So he's actually the person who thought of using the idea of CNNs for images. So he said that GANs are the most interesting idea in the last 10 years in ML. So if he has said that, that should have some credentials, I guess. No, credibility, I guess. So yeah. And this is a graph depicting the number of papers released on the topic GAN, like on the name of the paper, GANs is there. So these many papers, like you can see the growth rate. So as months move on, like so many papers get released each month. So yeah. So why is GANs? Why did GANs become this famous? Why is what can we do using GANs? So these are two applications of GANs. So you can look at these faces, right? Like look at these images of faces. These actually do look like real persons, right? So, but they are not. They're just faces generated using GANs. So this is pretty. They create like pretty clear images as well. So using so that's why GANs like so you can imagine how powerful GANs can be. And this is another example where the input image, if it's given in if the image is taken at a daytime, it converts the image into a nighttime image. And this is the ground truth, and then this is the output of our model. So this is the actual picture of the same scene at night, and this is the output our model generated. So you guys can compare, right? So this is actually pretty decent compared to the actual images. So yeah, so as GANs have various such applications, we just try and study them extensively. So how does a GAN work? How are we able to achieve this level of quality and this level of accuracy? So basically, GAN has two networks, and then these two networks compete against each other in what is known as a zero sum game. So what is a zero sum game? So let's say there are two players, and then one guy is tossing a coin. So if the result is a head, let's say player A wins, and if the result is a tail, let's say player B wins. Let's say player B wins. For each game, if player A wins, he'll get a let's say he'll get a bonus of +1, and then B will lose a point, lose -1, lose a -1. No, not lose -1. Like B will lose a point. In this case, the sum of the points of A and B, even after playing any number of games, the sum remains the same, right? So the profit and loss, profit incurred by A and loss incurred by B, if you add them up, just get zero. Not okay. The magnitude of profit and loss is the or same. So yeah, this is an image. So yeah, player A, they're playing a poker game. So player B wins. So all player B has now will now have four will now have 400, the 100 from all the three players, and then player A, C, D will lose and they'll have zero. So yeah, that's basically what a zero sum game is. So can you guys guess what these two networks of a GAN are? Like I just say that GANs are made up of two networks, right? And then I've explained a lot of models before as well. So can you just guess what the two networks that make up GANs? Did anyone answer or? Okay. Okay, I'll just go on. If anyone's answering, I'm not able to hear you guys properly. CNN. Okay. Okay. That's okay. Like, that's not exactly correct, but yeah, that's close, I guess. So yeah, exactly. Generative and discriminative models. So the GANs are made up of two networks called generator and discriminator. So what generator does is that it generates some data, and discriminator verifies whether the generated data is real or fake. So yeah. So I'll explain the working of GANs using a short story. So imagine you guys are at the Louvre in Paris. So and you guys are in front of a Mona and suddenly the current goes off, and then a thief just takes away Mona Lisa and goes. And so you guys, you don't want the rest of the world to know that someone stole the portrait. So you want you hired an artist and you're trying to replicate the portrait of Mona Lisa. So the names are a bit weird, I guess. So but I'll explain why these names come for the so so the artist first paints something, some random thing, and then the inspector says that no, this is not correct, so go and check again, go and paint again. So the artist now makes something else, but it's a bit better compared to this. Obviously, like this is just random lines. This image has a human form, I guess, but yeah, this is better, but not even close. So the inspector easily rejects the image and says that this is not acceptable. Go and make a better portrait for me. And then he makes something a bit better than the previous one, but obviously not even close now. So yeah, okay. And then again, the inspector says, no, this is obviously wrong. So try and make a better portrait. And now the artist makes a portrait which is quite close to the actual portrait. So and then the inspector now thinks. Previously, the inspector didn't even think. He just said that it's no, it's no, it's just go and make the portrait again. Now he thinks. He thinks whether I should I give or no. So, but he's leaning more towards no. So he says no. So the artist goes and makes the portrait again. So he makes a much better portrait. This is obviously this is just a black and white image. So this the officer is now confused. This is even more now confused. So he's in a dilemma. So he still says no, but yeah. So the artist now goes and makes another portrait, which which is which is pretty close. Like now the inspector can't even say no to the portrait which is made by the artist. So the portrait made by the artist is so convincing that the inspector gets fooled and accepts the portrait. So yeah, this is basically how a GAN works. So basically, I told that GANs have two networks, right? So generator will create an image. The discriminator will say whether that image is accepted or not. So and then we'll update the generator and discriminator and so on. So a GAN has two networks, as I told. So now what? How do GANs use these two networks? So yeah, generator produces fakes. Like the training data has some real images, and the generator produces fake images. That initially the generator produces fakes that are obvious, like the one I showed here. Like it produces fakes like this. So the discriminator directly says that no, and then the generator updates and then tries to make a better fake. So as the training progresses, the generator, as we saw, the artists become better and better, and then the quality, and then the fakes quality increases, and then the fakes actually start to fool the discriminator. So and then I forgot to mention this. Uh, if this is not obvious enough, the names is a combination of generator plus artist, and this name is a combination of discriminator plus inspector. So yeah, that's done. So yeah, so yeah, like as I told, initially the image is really bad, and then the discriminator says it's fake. This is the real data. So how does the generator say that the image is fake? Learn from it should compare it with an actual image and find the similarities. If it's too bad, it say that it's a fake, else say that it's real. So and then after that after some time it produces a somewhat of a better image. And then but obviously it's not I mean, look at these two, you can't even compare them, right? So the discriminator says no, and then after a lot of training, the generator actually creates something really close to the training data set. So this is how a generator this is how a generator and discriminator of a GAN work. So the structure, this is the architecture of a GAN. So as shown here, you'll have these are the real images which belong to the training set, and this is the fake image generated by the generator. So when any image is inputted into the discriminator, to classify that image as either a real image or a fake image. By real, what I mean by real is that the image comes from the training set. What I mean by fake is that the image is generated by the generator. So yeah, so the job of the discriminator is that if any image is inputted, its job is to find whether it's from the actual training set. So and then to create new fake images. So yeah, this is the structure of a GAN, and then the discriminator. The job of the discriminator, as I just mentioned, is to classify whether a given data is real or a fake. Classify in a sense the discriminator models that we visited earlier. So the discriminator gets its input from two sources. like from the training set, this is one set of input, and this is another set of input. So yeah, and a discriminator is trained by adjusting its parameter whenever it makes a wrong prediction. So what happens here is that we have the discriminator here, and then the discriminator predicts whether the image is a real image or a fake image. If the then we have the actual correct output, right? This is the output generated by our discriminator, and we know the correct output, right? We know a given image is, while we are training, we know whether a given image is coming from a training data set or the generator. So we design a loss function, and then if the discriminator predicts correctly, if the discriminator predicts a real as a real or a fake as a fake, we don't need to do anything. But if a discriminator does, if it does a mistake, or if it classifies a real image as a image generated by the generator, or the image generated by the image from the actual data set, we the loss, we'll find the gradients, we'll update the parameters of the discriminator. One important thing to note here is that while training the discriminator, we are back propagating to update the discriminator weights, while we'll not touch the parameters of the generator. The parameters of the generator will remain fixed when we're training a discriminator. That's an important point you should keep in mind. So yeah, the loss function of the discriminator, a combination of loss functions. So that are the two types of loss for the discriminator. So if it classifies the real image as a fake image, then that's a kind of a loss. And if it classifies the fake image as a real image, that's another kind of loss. So the loss function of the discriminator will be a combination of both of these losses. So yeah, and now comes the generator. The generator creates fake data by taking in feedback provided by the discriminator. So if the what the sole purpose of the generator is that it should try and fool the discriminator. It should make the discriminator confused as whether to classify the generated image as a real or a fake. So that's the goal of a generator, right? So how do we train the generator? We'll get a random image from the generator, and then we'll pass it on to the discriminator. We want the discriminator to classify this image as a real, as a real image. So that's what the aim of the generator is. So and based on whether the discriminator is making a correct prediction or not, we'll update the weights of the weights, and we'll update the parameters of the generator. So yeah, and then okay, this is done. So so how do we generate an image? How does a generator generates an image? So what we do is that yeah, sorry. So we take a random noise, like we take a Gaussian noise, maybe, like it can be any noise, and we'll do the exact opposite of what we did in a CNN. In CNNs, what we did is that we had an image, we tried to reduce it into some encoding of lesser dimension. Here, what we're doing is that you have a vector, you're trying to generate an image from that vector. So it's basically the opposite of convolution. So it's deconvolution. That process is known as deconvolution. Yeah, as I mentioned here, the generator produces an image through a process called deconvolution. So yeah, convolution, you have a 3x3 image, you have a 2x2 kernel, and after that, if you apply that kernel to that, you get a 2x2 image. That is convolution. And in deconvolution, you have a lesser sized image. You try to somehow generate a bigger sized image. So yeah, and then we sample a random noise and generate a fake data set, fake data instance, and then we input this fake data to the discriminator, and then depending on whether or not the discriminator gets fooled, we'll update the weights of the generator. So see, as the diagram explains, like you'll first you have a vector, you'll generate a sample, you'll pass the sample onto the discriminator, and the discriminator will classify that sample as a real or a fake. The objective of the discriminator is to classify it as a fake, but the objective of the generator is to make the discriminator classify it as a real image. So if the discriminator as a image, there is no issue. We don't need to do anything. But the problem comes when the discriminator correctly the the generated sample is in fake. So we'll calculate the loss function, and then we'll find the gradient, the parameters of the generator, and then we'll update the parameters of the generator. And then again, another important point is that while training the generator, we don't touch the parameters of the discriminator. Yeah. So you find the loss, find the gradients of the parameters of the generator with yeah, gradients of the loss with respect to the parameters of the generator, and then update the generator alone. You don't update the discriminator. So any idea on why we train only one network at a time? Why we don't train both these simultaneously or something? Any thoughts? Anyone? If you guys are saying anything, just please raise your hand. Yeah. Okay. So why we don't do that is that if we try to update both the generator and discriminator, both the models will kind of chase a moving target. We won't have a fixed target, and that's not sort of ideal. So that's why we train only one network at a time. And yeah, and yeah, I'll just go through these slides again. So if you guys have any doubt, just any doubts you can ask. It's fine. Like yeah. So yeah, GANs. The definition of GANs. There are two networks playing a zero-sum game, and then uh, each one network is a generator, one network is a discriminator. Generator first tries to produce an simple image, and then the discriminator classifies it as a fake, and then the generator tries again to perform better and produce a better portrait. So the story is that, and yeah, and in the training of generator and discriminator, and yeah. So any questions? Yeah. Can you speak a bit? I'm not able to. We are we are training. Yeah. 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 So yeah, question. So what happens if we just train the discriminator using the real world images? So what happens is that the discriminator will learn that the real world images are real, but it won't ever come across a fake image. So it won't even know what a fake is. So even if you input some random thing, it'll classify it as a real. So you won't be able to train the generator properly. So sorry, can you repeat again? Yeah. Yeah, like while training the discriminator, we know the actual output, we know the output generated by the discriminator, and then we'll find the loss function. If the discriminator identifies the image generated by the generator as a fake, then the loss value of the loss function will be 0. Else it'll be something. So we'll update it. So yeah. Any other questions from anyone else? Yeah, exactly. Yeah. Anyone else you got it? Yeah. So yeah. So when a discriminator classifies, so let's say you have a image generated by the generator. Like when a discriminator classifies that as a fake, that when the discriminator classifies this image as a fake, the generator won't get updated. So, but and then if it like it's contrasting, right, for the discriminator and the generator. You get it? I don't get your question actually. Can you repeat? Yeah, zero sum game. Yeah, yeah. So as I explained here, right? So you have a sample, that sample generated by the generator, and then you pass it on to the discriminator. You and then you get the output, and the output, if it's real, the discriminator is performing well, right? Well, your discriminator is performing well. Sorry, if it's real, the discriminator is performing badly, right? The generator is performing well. So if the discriminator identifies correctly, uh, uh, that you're updating the weights of the generator. So like if the discriminator identifies it correctly, it's the loss of the generator. Like if the discriminator identifies what I'm repeating same thing again. Sorry. If the discriminator wins, the generator loses, right? Like if the discriminator classifies it as a correct image, the generator is wrong. So if the discriminator is correct, the generator is wrong, and vice versa. If the generator is correct, the discriminator is wrong. Yeah, kind of like that. Yeah, yeah. Mm. Yeah, 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 yeah. Actually, I didn't like fully explain how you train the GAN. I just explained how you train the discriminator. I explained how you train the generator. I actually didn't still didn't explain how you train the whole model. Like uh, whether you train the discriminator first or generator first. I didn't explain that, right? If that is explained, I guess your question will be clear. Yeah. That's your wish. You can keep it as 0, maybe. You can keep the real one, the label for real images as 1, and fake images as 0. It doesn't matter basically. No, no, no. At one forward pass, we'll either give the image by the generator or the image from the real world. Yeah. Yeah. Any other questions? Anyone else? So yeah, as is done, next Saran will take the continuation of this topic after some 5 minutes. So yeah, thank you for your patience.
Hello. 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 We'll start in a minute. Hello. So, hello everyone. I'm Saran. I'm from the CS. I'm a editor and a project member at an analytic club. So I'll be doing the second part of the session from where Gokul left off. So yeah, the first topic that we'll be doing, the first topic that we'll be covering is how do you train a GAN? So this is basically directly connected to the question that the last person asked. So go covered how you train the discriminator and the generator separately. So, but the GAN is a combination of both of those. So we'll be looking at how you train both of those combined. So The picture you see here is basically just a recap of what was done, the rough architecture of what a GAN is. So you can see that uh, there is a latent vector here that is basically the noise that you first give as input. This is passed to the generator network, which then generates the generated image. That's a fake. And on the other side, you see the real image data set. So you send both of these as the training data set to the discriminator network, which then makes a prediction whether it's a real image or a generated image. Basically, if it came from this side or from that side. So, yeah. So, yeah, this is the rough outline of the training. Yeah, you can see that oh sorry. Yeah. So if you notice the architecture, there are some key points, key observations that you have to make. First of all, the output of the discriminator is directly connected to both the losses. So there is two types of losses, discriminator loss and the generator loss. So basically, it's similar to how a neural network, how you train a neural network. You calculate as a loss function, and then you try to reduce that loss by back propagation. So here, since there are two neural networks, that is a generator and the discriminator, there are two loss functions. So, but the weird thing here is, in a general neural network, the neural network's out is used to calculate the loss function, and the loss function is used to better train the neural network. But here what happens is, the discriminator is connected to both of the losses, and the generator's output is not even related to the, is not even connected to the generator loss. So the discriminator's output basically controls both the loss functions. So that is one key point you need to notice. And after the discriminator makes a classification, so if a real image was passed into the discriminator, the discriminator should ideally give output as 1. So that is the input image was real, and if it was fake, it should give output as 0. So based on the discriminator's output, you can calculate both those losses and use those losses to back propagate and update the weights of both these neural networks and make it better. Yeah, as I said, if the discriminator gets fooled, so it gives the wrong answer. In that case, the generator loss is lower. Like, loss is high when the model isn't appropriate, it's giving wrong answers. But if the discriminator gets fooled, that means the generator has done a good job that it's supposed to do, generating a very convincing fake. So if the discriminator gets full, the loss is low, and the back propagation, the weights don't get updated much in the generator because it's already doing a good job. But since there is still some finite loss, it needs to update it a bit more, but it will be very low. On the other hand, if the discriminator if the discriminator doesn't get fooled, so it actually exactly detects a fake image, in that case there is a room of improvement that can be done on the generator. So in that case, obviously the generator loss will be quite high. So during back propagation, there is significant changing of weights that's happening in the generator neural network. So yeah, this is basically the idea, like improving the generator and the discriminator, the neural networks. And as you can see, I've written the loss functions to the right of the boxes. If you can't see that, it's fine, like it'll be explained later. So those are just some mathematical expressions which I'll be explaining towards the end. So yeah, first, this is just a recap of what Gokul did. Uh, First step is to train the discriminator, because you want someone to detect if your image is fake or real. So what you do is, again, you send in the training data set, real images and fake images. You get the loss functions, and in this case, only one of the loss function, that is the discriminated loss function, that loss is back propagated, and that back propagation is used to update the weights of the discriminator. So, and during this process, while the discriminator is training, you can see that the generator, there's a log sign on it. That essentially means whatever loss is being back propagated, that is not being used to change the weights of the generator. The generator model is kept constant. Basically, the generator's ability is maintained constant while the discriminator is being trained. So if the generator was quite bad, if its ability to generate good fake images, if its ability to detect fake images was bad, it's maintained as it is while the discriminator is being trained. So you keep it fixed because if you keep both moving, it's like as Gokul said, like trying to hit a moving target, you the training won't be proper. So you keep this fixed and trying to train the discriminator better, and this thing goes back and forth. So yeah, this is just to give you an intuitive idea of what a discriminator is. Basically, you give an image as an input to a discriminator, and it basically gives you the class if it's fake or real. So this is the most simplest form of a general classifier in machine learning. It classifies an image as either as real or fake. It, it tries to distinguish the real data from the data created by the generator. And now for training the discriminator, the inputs, the training data set that you're supposed to give are the real data, that is the real images. You need to have a sample of real images, and these are used as positive examples. So these are associated with the label 1, that it's a real image. And you also use fake images as negative examples. So these fake images are generated by the generator which we build. So we'll see how the generator generates those fake images. But yeah, these are the inputs that are supposed to be given during training the discriminator. So yeah, in this figure, you can see the 2 sample boxes. And again, this is the same thing. The generator is fixed while the discriminator is being trained. And the observation that we made, that the discriminator is directly connected to those 2 loss functions. Yeah, and the generator loss is ignored during back propagation. Only the discriminator loss is used to update the weights of the discriminator. Now, this is basically the algorithm of how the discriminator is trained. So it classifies both real and fake data from the generator. And if the discriminator makes a mistake, it gets a penalty for misclassifying a real image as fake or a fake image as real. And using this loss, it does back propagation to update the weights of the network and becomes better this way. So in the next section, we'll see how a generator basically works, and like it'll give you a bit more intuition on what a generator is. So yeah, so this is, so what you have here is you can see that vector which you had written a couple of slides back. Yeah, you can see this latent vector which is mentioned here. So I'll be explaining what the latent vector is. Yeah, so first of all, you want the generator to generate a fake image. So how you do that is basically you initialize a vector which is called the latent vector. I'll explain why it's called the latent vector. Basically, it's just a single dimension vector, a row vector with any number of elements. Generally, it's around 50 to 100 elements in that vector. So you might ask, and initially we just initialize it to any random set of numbers, and it's normally taken. It normally belongs to a Gaussian distribution, specifically a normal Gaussian distribution. So the average of all these numbers is 0, and the standard deviation is 1. So generally, you initialize it to something like that, but still they are random numbers. So what happens is you feed this vector which you initialize with random numbers to your generator. So the generator is basically a neural network. Like it has a combination of convolution layers, max pooling layers, which Gokul mentioned. So what the generator does, it takes this single dimensional vector and makes it into a large image. So suppose this vector is 100 cross 1 vector. So, and the size of the image, all the real image data set is like 224 cross 224, 448 cross 448. This generator network is basically responsible for converting this vector to an image of that dimension. So you might see that suppose you assume that the GAN is completely trained. Okay, so all the weights of the generator and the discriminator are fixed. So now if you go inside and you want to see how the latent vector, which you can actually control, is mapped to an image that's produced by the generator, you can see some very interesting thing. Like if you see here, the first three values of the, suppose you want you define the latent vector to be 0 0.3, 0 0.2, minus 0.6, and so on. And your generator after training, suppose this is like a GAN which is being trained to generate fake images of cups. So after completing training, you suppose you give Z as these values and so on. The generator comes up with a blue round cup, for example. So it's generated it's like pretty accurate. It's actually a cup, but with certain features. It's blue and round. So now suppose you change Z to minus 0.1, 0.1, 0.2, and so on. So you can see that you have changed these numbers, and still you have no idea what these numbers mean. Like you don't know what the first number represents, what the second number represents. You just give it some numbers, and the generator outputs a yellow tall cup. So what's going on here? So you input a vector and you get an image, and you can see the features like blue converts to yellow, and round it becomes tall. So this is exactly the issue. This is one of the issues with deep learning. You don't know what's going on underneath. You just know during training, it's somehow the generator is trying to connect these numbers to certain features. You don't know whether if the first number maps to color, the second number maps to a shape. You don't know anything because they were a combination of numbers might map to color. Like we don't know exactly. But the network, neural network, takes care of that, and it basically gives you the required output image. So now I think you'll be able to understand why a latent vector is called so, because latent basically means hidden or concealed. So inside these set of numbers, the features of the cup are hidden in it. You don't know which feature belongs to which number or which set of numbers. You have absolutely no idea. But the features are hidden somewhere in these numbers. That's why this vector is called a latent vector. So here you can see is the basically the architecture of the generator. So if you see the code of a GAN, the code of a GAN, you'll be able to see this implemented in it. So you can get a rough idea, like the first input is 100 cross 1 vector. That's basically a latent vector. So it has some 100 random numbers. So at each step, you can see the dimension being increased. So this is the opposite of convolution, and it's called deconvolution. So what you're doing is your final output should be an image of say here the size is 64 cross 64 cross 3. So that basically means your output should be a 64 cross 64 pixels, and the 3 indicates RGB. So it's a colored picture. So from this unidimensional vector, hello, oh, yeah. From this unidimensional vector of 100 random numbers, you're somehow you're somehow coming up with a larger uh, dimension, and that's an image. So yeah, this is what a generator does. It This process is called upsampling. So it's basically increasing the dimensions at each step, and finally you get the image. The generated fake image is the last image there, and you can view it you can view it as a classifier in reverse. So in a classifier, what happens is you have that image as the input, and you have to decide that if that image belongs to class 1, class 2. Like say there is an image of a dog, you want to classify it belongs to what breed. So say there are 10 breeds which you want to classify into. So there's an image of the dog, and this here would be a size 10 cross 1 vector. So each element of the vector will be the probability that the dog belongs to this class 1. The dog belongs to class 1, the dog belongs to class 2, all those probabilities. So clearly it's like the reverse of a classifier. Yeah, now we look at how a generator is trained. Again, this was already explained before. This is just a recap. Uh, the generator's weights are updated by backpropagating the generator loss. And the generator loss is calculated from the discriminator's output. But note that the discriminator is locked here. Like the same thing before the generator is locked, now the discriminator is locked. So you calculate the generator loss, do backpropagation, but do not change the weights of the discriminator. And when you reach here, these backpropagation, these gradients are used to change the weights of the generator. So the generator starts getting better, becoming a better model. Yeah, and you already saw that for training a discriminator, the training data set that you're supposed to give are real images and the generated fake images, which were generated by the generator. So for training the generator, you need some more. Hello. Training the generator is a bit more involved than training a discriminator. A discriminator is basically a normal classifier. So you just need to give it labeled data like real images, and you have to tell it is 1. You have to give some fake images and tell it 0. That is straightforward. But a generator is something different, right? So the things, the inputs that you need to give are first the random input, the latent vector. So, and you need the generator network. So you pass this random input, that is a latent vector, to the generator, and it gives you an image, an upsampled. It basically upsamples the random input and gives you a image that is of the same dimension as the real image, and that is the fake. Now you need a discriminator network also. So that takes that fake image and makes a classification. Either this is real or fake. Now that is the discriminator output. And based on if the output is correct or wrong. So if the discriminator makes a correct output, that it basically exactly finds out if it's a fake. Hello. Yeah, and if the discriminator finds out if the fake image is a fake, then the generator loss is going to be high, and correspondingly the weights of the generator are updated more in order to get better. But if the discriminator output it doesn't manage to prove it's fake, it says it's real, that means the generator is doing a pretty good job of fooling the discriminator. So weights aren't updated as much, and the generator loss is low. Yeah, and this is basically the algorithm of training a generator. Generate a random noise, give it to the generator, and that produces a fake image, an upsampled fake image. Now pass that fake image to the discriminator, and that classifies it as either a real or fake. Now, based on the accuracy of this decision, whether the discriminator identified it or not, you calculate the generator loss. So, if the discriminator identifies a fake, generator losses will be high, else it will be low. And based on this generator loss, you back propagate it to alter the weights of the generator. And the discriminator is kept fixed during this time. Yeah, and you can see change only the generator weights during this time. Now this is one iteration of a generator training. So yeah, now uh, this is the main part. How do we train a GAN as a whole? So GAN is a combination of two neural networks, right? So training a single neural network like a discriminator is fairly straightforward. Giving it real images, giving it fake images. So how do you train two neural networks simultaneously? So the process is called alternate training. So the name is fairly intuitive. So what happens is these steps happen in alternate periods. First, the discriminator trains for one or more epochs. Epoch is basically iterations through the data. So the discriminator trains for one or more epochs. Then the generator trains for one or more epochs. And these two steps are repeated to continuously train the generator and the discriminator. Now, yeah, step one is training the discriminator on real data. So first, you have access to real data initially. So what you do is, this is a supervised learning phase. So you give a real image and tell the neural network that this is real. So you give labeled data. So you give the image and it's labeled as one. So the discriminator learns the features of what makes an image real during this phase. The second step is you start generating fakes slowly. So beginning, the noise, the latent vector is completely random, and the weights of the generator also completely random. So the image, the fake image that you get is like basically nothing. It's just noise, random noise. So you feed this to the discriminator and tell this is fake, this is not real. Now what you do is, now after you send these fake images to the discriminator, it gives you an output. Like you'll know whether the discriminator gets fooled or not. If it gets fooled, that means your generator is pretty good. And if it is not getting fooled, that means you have to make some changes. That is basically calculate the generator loss, back propagate it, and update the weights of the generator. So that is basically making the generator generate a better fix. Yeah, and these three steps, you just repeat it for a few more epochs. Now the thing that makes training a GAN different from a general neural network is, in a general neural network, if you increase the number of epochs, you can expect the accuracy of the model to increase steadily. But not continuously. After a while, there's some overfitting, but the accuracy generally constantly increases. But here, uh, and yeah, in GANs, the problem is, I will go to the problem later, but the point you need to remember is, you need to keep an eye on the fake data that's being generated continuously. Like after each epoch, you need to see the quality of the fakes. So if it's convincing enough for you, like you check these manually. So if it is convincing enough, you can basically stop the training, because even after it's convincingly good, you still continue training, you'll come across some issues, which I'll be discussing now. Yeah, hello. Yeah, and before that, let me just go over some explanation of the loss function for both these neural networks, the discriminator and the generator. So first, the discriminator, it's basically a classifier. So it outputs a single value. That is, you call it d of x, where x is the input. Suppose if it's a real image, d of x is the probability that x is a real image. That's being uh, determined by the discriminator. So our objective and like d of x is that, and you can see there's a d of g of z there. G of z, you can, I think you might remember z is the latent vector. So g of z should be the fake generated by the generator. And d of g of z is the probability that the fake image is classified as real. So if d of x, so if d of x is 1, that means the discriminator thinks this is real. And if d of x is 0, that means the discriminator thinks it's a fake. Similar thing goes for g of z also. If d of g of z is 1, that means the discriminator is actually getting fooled. So it's thinking the generated fake is real. And if d of g of z is 0, that means the discriminator is thinking the fake image is fake. So that is correct. So the objective function can be written in this form. So this is generally, this is called binary cross entropy loss, but the name is not important. Basically what's happening here is, first on the left hand side, you can see this is just a function's name, v of d. And on the right hand side, the first expression is log d of x. So what it's doing is, you want, ideally, this is a loss function for the yeah, this is a loss function for the discriminator. So ideally, you want the discriminator to identify real images as real. So you want d of x to be 1, right? So because x is a real image, so d of x should be 1 ideally. So when, and if x is, and if d of x is 0, the log term tends to minus infinity. And if d of x is 1, the log of d of x tends to 0. So as you can see, ideally we should be maximizing the first term, right? And the second term, it seems a bit more complicated, but it's really simple. So you can see instead of log d of x, it's log 1 minus that. So what happens is, you want the discriminator to identify a image as fake. So you want d of g of z to be 0, right? Because g of z is fake image. So the probability that the fake image is fake, you want it to be ideally 0. So 1 minus 0 is 1, and log of 1 is again 0. And if d of g of z is 1, that is, the discriminator is identifying the fake image as real. So 1 minus 1 becomes 0, and log of 0 again tends to minus infinity. So basically, you want to maximize both these terms of this expression. So that's what's written here, max, and the d at the bottom represents, like with respect to the discriminator. For the discriminator, you need to maximize this whole expression. So that's basically what this is the loss function for the discriminator. And the loss function for the generator is fairly simple. So yeah, what you're doing here is, for the generator, you want the fake image that it generates to be identified as real by the discriminator. So d of g of z should be 1. And yeah, because g of z is a fake image, and you want, you can see the g here, that basically says that you're doing this with respect to the generator. For the generator, you want d of g of z to be 1, basically saying the fake image should be identified as real. And in that case, 1 minus 1 becomes 0, and log of 0 tends to minus infinity. So here you want to minimize the expression on the right, and that's why the min word is written there. And you might ask, why can't I just have log d of g of z and maximize that? That can also be done. And in fact, practically, that is better. Having the minimization function as log d of g of z and maximizing it is better. Uh, Due to you, if you use this function, you'll get issues with during training. Like the gradients, while you're training, the gradients become 0. like after a while. And when gradient becomes 0, that means there's no change happening and your model does not improve. That's an issue that might come if you use this loss function. So instead you can use log d of g of z and maximize it. So this is the overall loss function for our GAN model. So you can see that that expression on the right is the exact same as the loss function of the discriminator. But on the left hand side, you can see some changes. So basically, let's see min g, let's see that part. So what this means is with respect to the generator, you want to minimize the RHS. And that makes sense because with respect to the generator, you want d of g of z to be 1 for the fakes to be identified as real. So that term, it becomes 1 log 1 minus 1 and it tends to minus infinity. And this the first term doesn't even matter for the generator because uh, the generator doesn't take real images as input. So the first term doesn't matter. So the second term, basically you're minimizing it. So you're minimizing the overall expression for the generator. So min g represents that. Max d, it basically says with respect to the discriminator, you want d of you uh, with respect to the discriminator, the RHS is basically the same as the discriminator loss function. So you're making d of x 1 and you're making d of g of z 0. So essentially you're maximizing the whole RHS. So that's basically the notation that's given on the LHS. So yeah, and what's written here is basically what we have seen. The name of the technique is called alternating gradient descent. That is, you update the weights of the discriminator, then you update the weights of the generator, and so on. You alternate between these two. Yeah, and while updating one neural network, you keep the other neural network's weights fixed. Yeah, and you can see we train both networks in alternating steps until the generator produces good quality images. So now we'll see why we need to stop when it starts producing good quality images. Yeah, so that we'll come to that. We'll come to that problem next. So the first most common problem you can face while training a GAN is named mode collapse. So, so So mode collapse happens when the generator starts generating very small amount of unique images and the discriminator is continuously getting fooled by it. So, let me show you what exactly that means. You can see in this image that these are generated fakes, right? So what is happening is you may see the faces are like pretty similar or exactly same everywhere. It's just like smashing the face into some random background essentially. So, and the discriminator is actually getting fooled by this. So this is obtained at the end of training, and you can see this is not good at all, right? This does not represent a real image. But the more tricky problem is it's generating the same image face again and again. Like why does this happen? Like the fundamental reason, uh, the fundamental the fundamental reason why we use GANs is to generate fake images, a wide variety of fake images. Yeah, but this is against that, right? Like this is just generating a very small amount of fake images that has no diversity and is just like aimed at fooling the discriminator. Like that is not the objective that we want. So you might ask like why this happens. So while training a GAN, you basically first train the discriminator, you train the generator and so on. So first, initially the discriminator is also bad, the generator is also bad. So what happens is you start training the discriminator, it starts getting slowly better. You start training the generator, that also gets slowly better. But consider the scenario where the generator starts it's becoming better at a faster rate than the discriminator. So there'll be a point where the discriminator is not well trained enough, right? It's not able to perfectly detect yet, but the generator is like generating fakes that are actually starts fooling the discriminator. So so you might understand what happens next. So the generator is constantly fooling the discriminator using the same set of images, very limited a set of fakes that is being used, and the discriminator is continuously getting fooled. So no model is getting better here. The generator is staying stagnant. It's like content with what it's already done. Just these small set of fakes, and it's constantly fooling the discriminator. So this is the reason why mode collapse happens, and it's fairly common. So you need to be sure that you need to make sure that mode collapse doesn't happen. So there are a few measures that you can take. Yeah, and the case I told you is one example where the generator is not that good, but it is better than the discriminator, and so it starts doing that. But the other case might uh, the discriminator is like pretty good, but the generator finds just one really good image, one really good fake, and it gives it to the discriminator, and the discriminator gets fooled. So it starts giving it again and again. Even that case is possible. So even though the discriminator is very well trained, the generator just finds one very good fake that it has generated and constantly passes it to the discriminator. In that case also, we don't get there's no diversity in the generated fakes, which is what actually. And the second fairly common problem is convergence failure. Like this is pretty intuitive. So the discriminator and the generator are constantly being trained. So at some point, the generator becomes very good and it starts generating fakes that cannot be detected by the discriminator. So let's see what happens at this point. Let's say after. Hello. Yeah. Let's say after you train the GAN for some time, you start getting fake images like this. Like this is pretty good, right? But what starts happening if you continue training it? Okay, you don't stop it. What happens is now you give this fake image as an input to the discriminator. Now the discriminator has to make a decision whether this is real or fake. But the discriminator, like this looks real, and the discriminator gets confused because even though it looks real, it didn't come from the original training data set and it doesn't know that. So it just sees a real image, and the probability is essentially half. Either this very real looking image came from the real data set or has been generated by the generator fakely. So obviously the discriminator can't do much. It can just guess, and that's exactly what it does. It just guesses whether it's real or not. And the problem with this, there's a half probability of it telling that this image is fake, or a half probability of telling this image is actually real. So and this is pretty bad because when suppose in the previous in the previous image, this is clearly a fake, and we know that. But this discriminator starts guessing it, and suppose it tells this image is real all the time. So what's happening is that's the wrong answer, right? So you're essentially uh, and we already saw that the generator is basically connected to the discriminator's output. So whatever, if the output of the discriminator is correct, then the generator can be better trained using that feedback. But if the feedback from the discriminator itself is wrong, then you're training generator in a wrong way. So the generator, after this point, what happens is the quality of fakes start deteriorating, right? And that's the reason why we stop training after you see a reasonable quality of fake image. So the convergence. So this term is called convergence. That is so. So convergence basically you can understand it, get a better intuition with the help of the loss function. You can see in this loss function that we wanted to minimize the RHS with respect to the generator. We also wanted to maximize the RHS with respect to the discriminator. So you basically you basically want to minimize and maximize the same expression. So what ends up happening is, so suppose you minimize, so you start from a high value, you start minimizing it. So you'll reach a halfway point, and that is the point ideally at which you should stop training, because after that it just starts going in the opposite direction and you start getting poor quality fakes. So identifying this convergence point or halfway point is hard during training. So you actually have to manually see the quality of fakes at each point of time. So this is what's given in the last sentence. So convergence is like a sharp peak of a hill in case of a GAN. So neural networks, it's like a steeply increasing hill and it slows down after a while. But in a GAN, the peak is very sharp. So you run more and more epochs, you actually climb the hill and the model becomes better. But after you cross the peak, the model starts deteriorating. Hello. Yeah, so finding this sharp peak is a challenge while training GANs. So yeah. So yeah, like this covers the whole basic idea of how you train a GAN. So any doubts? Okay, so now I'll just show you an implementation of an actual GAN that's been produced. Hello. Yeah. So DC GAN is one type of a GAN, right? And it stands for Deep Convolutional GAN, Generative Adversarial Network. So what you have attempted to do here is generate fake images of celebrity using a large database of real celebrity faces. So I'll just I will we will be sharing the code with you. You will have access to this notebook. Now I'll just be showing how the quality of fake images progresses as you train more and more. So this is yeah. This is just the code where we're implementing DC GAN, and you can see like we have used the data set that's called Celiba something, yeah, and we are loading the data set. So you can see here, this is just the this is basically the real data set. So these are pictures of real celebrity faces, and one thing you might notice is that the images are small. This is because larger your image, the more time it takes to train the neural network. So we ran this model for around books, and that only took around 40 minutes. And these are just like very small images. So if you have a high HD image, it might take even weeks. Even with a supercomputer, it might take weeks to fully train the model. So we are using small images just for the sake of this session. And you like this, basically I'll just show you the major parts of the program. So you can see here, this is the generator. So we create a generator class. It's fairly short. So all these lines where you can see con transpose 2D, those essentially are convolutional layers. So you can see there are several convolutional layers in our in our generator function. Like I hope you remember the architecture of the generator which I showed before. You start the 100 cross 1 vector, and you move to the final picture, and in between there are several stages. So each stage is a convolutional layer. So, and this is a reverse convolutional layer. So at each stage you're increasing the size, the dimensions of the vector you're having, and finally it reaches the image size. And yeah, this code, this whole set of code is for creating the generator architecture. Now this code is for creating the architecture of the discriminator. And again, here also you can see this conv2d. Basically, this is the Python code for creating a convolutional layer. And in this case, what happens is we start from an image. We have convolutional layers at each step. And here, hello, yeah. And in this discriminator architecture that we have used, you can see there are 1, 2, 3, 4. There are 5 and this is fairly common. So you start from an image. You start from an image, and you have 5 hello, yeah. You start from an image, and you have 5 convolution layers. At each stage, what a convolutional layer does is it takes a larger image, makes it a smaller image, while trying to preserve the features that are in the original image. Obviously, when you make it smaller and smaller, you lose some part of information. But that is a trade-off that you're willing to accept in order to reduce the time complexity, right? So finally, like, you make the large image smaller and smaller using convolutional layers. Hello. So finally, the large image is converted to the probabilities. Like, is it real or is it fake? And this is basically the Python code for creating that architecture of the discriminator. Now, these are just loss function. You can see BCE. So I mentioned the word binary cross entropy loss. This basically creates that loss function, and this is an inbuilt function in Python. So you can use that. I mean, everything is inbuilt in Python. So yeah. And these are just optimizers in order to increase the speed of training. And now this hello, yeah, this part of the code is where the training happens. So I think here you'll be able to see the comments. So you see, first you see update the discriminator network. Hello. We first train the discriminator with the real image data set. Hello. Hello. Yeah. And hello. Yeah. And that's what's happening here. Hello. You first train it with an all real image data set, and you do a forward pass. That is, you see all the real images, and you capture information of what makes an image real during this forward pass, and you calculate the loss. So suppose, yeah, you just see the input you give to this criterion is the loss function. So the inputs you give are output and label. Output is basically the image, and label whether the discriminator has classified it as real or fake. And this code is calculating the gradients for back propagation and updating the discriminator's weight to improve it. Now the next, as a slide, is training with an all fake batch. So this is basically just implementation detail. You're creating a set batch of latent vectors, and you can see here the random function being used. So as I said, the latent vectors is completely random, right? And using this noise, that is a latent vector, you generate the fake image by inputting it in the generator network. Hello. Yeah. So this fake is the fake image that's generated. Now you classify the fake image. Like you, hello, like you input this fake image to the discriminator and just observe its output, whether it's true or not. And based on that, you train the generator. Train the discriminator. Like this whole thing is just for training the discriminator. Train with the real batch, train with the fake batch. The next step is updating the generator network. And here you can see the fake labels are used because uh, the fa- uh, the images generated by the generator are fake, and you know that. So, but you give the label of, instead of 1, you give it 0, and you try to fool the display. No, no, battery half is there. So what is it? Yeah. So this part is training the generator. This part is training the discriminator. As you can see, like all this thing is just the summary of each epoch. You can see the loss is being here. So yeah, the loss the loss isn't strictly decreasing. It actually alternates until it becomes constant. Like that's unique about GAN. So you can see we have done 9 epochs, and let's just see the result. Now this is a graph for the loss function over a period of time. The blue one indicates generated loss, D indicates generated loss. You can see, initially it's very high and it becomes quite low at the end. And yeah, let's now this animation will illustrate how the fake images are being generated. So initially you can see this is completely noise generated from the random latent vector. This is completely random values, and clearly this is noise. But immediately you start seeing some resemblance, and as the training progresses, you can see that it starts resembling somewhat close to an actual real face. And after this is the image, this is the final generated fake images, and at the bottom you can see a comparison. So yeah, these are real images. And you can yeah you can hello yeah you can see the fake. Some of them are actually close, and most of them are still bad. But for 9 epochs, this is actually a really good result. So some images are very closely resemble a real face. So yeah, so this was a implementation of a type of GAN called DC GANs. So I hope you got a good understanding of GANs in this stop here. Thank you.
Okay, guys. So thanks for attending. So if you have any questions, please stay back. We'll be here to clarify all your doubts, and we'll be having a second session tomorrow at 3 p.m. So please join back. It'll be like more hands-on session, and it'll be more interesting because we'll be looking at several GANs and what they can achieve. Okay. Thanks. Yeah, yeah. Please go ahead.
Yes. Yeah. Can you repeat? Mm. Mm. Fake images. Like randomly. No, but the fake images are being generated by the generator, right? So you're training the discriminator and you're training the generator. Yes. You're saying you're generating all the fake images and then inputting both of these to the